everyone. My name is Cao. Today my topic is light-driven metal-free direct deoxygenation of alcohols under mild conditions. As we all know, coal, petroleum, and natural gas, as the most important fossil fuel, account for about 18% of the Earth's energy. However, in recent years, with the rapid consumption of fossil fuels, there is an urgent need for alternatives. Biomass energy is the second largest energy source, in addition to fossil energy. It is particularly important to replace fossil energy with biomass energy. Therefore, the selective functionalization of biomass resource has attracted widespread attention. In the early years, people simply modified and studied biomass resource, such as hydrogen bond donors and acceptors. But in recent years, selective defunctionalization seems more and more popular, especially accurate removal of functional groups. Because hydroxy groups are widely present in biomass molecules, it is necessary for the selective defunctionalization of hydroxy groups, especially deoxygenation of alcohols. But there are still some challenges in deoxygenation of alcohols, mainly in the following aspects. First, in terms of energy, alcohol has stronger cell bond dissociation energy. In addition, for selectivity, many biomass molecules contain two or more hydroxy groups. It is difficult to remove a special one. And finally, also consider the cost of catalyst and mild reaction conditions. So it is necessary to develop new catalysts and mild conditions to achieve high efficiency and selectivity. At the beginning, the deoxygenation of alcohols was mainly by converting it into an intermediate, then get the desired product, which is called indirect deoxygenation. The indirect deoxygenation method can be divided into radical process and ionic process. This method suffered from multi-step conversions that resulted in poor staple efficiency and atom efficiency. Therefore, in recent years, many metal-catalyzed direct deoxygenation reactions of alcohols have been developed, but this method requires high temperature. Also, the later developed metal photocatalytic method reducing the reaction temperature. It is still cannot avoid the use of expensive metal catalysts, which have greatly limited their application. So how to simplify the reaction conditions of alcohol deoxygenation? First, a direct deoxygenation method is required. Then, in order to reduce costs, the reaction process should avoid the use of metal catalysts. And finally, the reaction condition should be mild. Inspired by our previous work on using hydrogen and traceless metals for homo and cross coupling, and as metal-free hydrogen atom transfer reductants for pinnacle coupling enabled by light. We herein disclose the first light-driven metal-free direct deoxygenation of alcohols with hydrogen through cell bond cleavage under mild conditions. To validate our hypothesis, the direct deoxygenation of 1L with hydrogen was carried out under UV light with potassium hydroxide as base and dimethyl as solvent under air and room temperature. The desired product 3L was obtained in 63% yield after 24 hours. And then other light sources, different base, different solvents, and The amount of hydrogen reaction time were investigated. By optimizing the reaction, we can obtain the best conditions using UV light for equivalent of hydrogen, 2 equivalents of base, 1 milliliter DMSO for 18 hours at room temperature on the air. With the optimized reaction conditions in hand, the substrate scope of primary benzyl alcohols was investigated. To our delight, different benzyl alcohols with electrodonating or electro-withdrawing groups were successfully deoxygenated to afford the corresponding aromatics in moderate to good yields. Multi-substituted substrates and polycyclic heterocyclic substrates could be well tolerated in the reaction. Then various secondary benzyl alcohols were studied. Alkyl, aryl, heterocyclic secondary alcohol were successfully deoxygenated to afford the corresponding products. When a bromine-containing substrate was used, the CBr bond also cleavage, which was consistent with literature. Pinnacle substrates has also been studied. When using the pinnacle substrates, the selective deoxygenation occurred at the benzyl position. Lignin model compounds were tested under the standard conditions. The corresponding aromatics and phenols were obtained. In order to understand the mechanism of this reaction, some control experiments were performed. Firstly, we use dimethyl sulfur instead of hydrogen as the reducing agent for this deoxygenation reaction, and the desired product was obtained in 81% yield. The result indicates that DMS may be intermediate in the reaction process. Secondly, we performed the reaction with deuterated hydrogen under the standard conditions, and the deoxygenation product D3L was obtained in 19% yield, with about 16.5% deuteration at the benzyl position. Thirdly, free radical trap experiments were performed. When 1 or 3 equivalents of tempo was added into the reaction system under standard conditions, the reaction still could deliver 17.6 and 16.2% yield of the deoxygenation products. The results indicate that the reaction may not be a free radical process. Finally, with aldehyde as raw material, only a small amount of corresponding product was obtained in the presence of hydrogen and DMS, showing that aldehyde may not be an intermediate in this reaction. Based on the mechanistical studies above, we proposed a plausible reaction mechanism. Firstly, DMS is in suits generated from the reaction of DMSO with hydrogen enabled by light, meanwhile releasing nitrogen, hydrogen, and water. Then light-promoted DMS reacts with oxygenation to form intermediate A, which reacts with alcohol 1 in the presence of base to provide the intermediate B. The release of oxygen and DMSO from intermediate B results in the carbonyl intermediate C. Finally, hydrogen proton abstraction from water by intermediate C gives the desired product 3. In conclusion, we described a photo-induced metal-free direct deoxygenation of alcohols with hydrogen and room temperature on the air atmosphere. This strategy has the following highlights. 1. Metal-free direct deoxygenation of alcohols enabled by light. 2. One-step conversion at room temperature and on the air. 3. Traceless non-toxic nitrogen, hydrogen and byproducts. 4. Broad substrate scope and wide functional group compatibility. 5. Converting lignin models into simple aromatics. And this is my big picture full paper. Thank you very much.